So once again, I welcome you all to the webinar session hosted by Mirabilis Design on mapping SysML to hardware architecture. So we'll be taking a quick look at the agenda I have prepared for this session. So first, we will be looking at three use cases, starting off with an example of an infotainment system modeled in VisualSim Architect, which is to determine the system limit. So we'll be looking at what is the maximum traffic that can be sent through the interface, what is the maximum throughput or the throughput required to satisfy the requirements of the application, whether what is the maximum power consumed by the chip. So those will be tested to the maximum limit to determine what are the capabilities of the design. And second use case, we'll be looking at how to design an SoC system for multimedia application where we have stringent requirements. So both power and performance requirement has to be met. And as a third use case, we'll be looking at executing automotive software in the presence of failure. So we will compare the simulation results with a normal mode of operation and also with that in the presence of failure, so that we can see whether the application can run smoothly even in the presence of a failure. And then we will look at the design process and methodology, where we look at how we use or capture details from existing SysML models and bring it to VisualSim Architect to do detailed architecture exploration and do analysis like inject failures and see how the system behaves under those situations. And at last, we will look at a little bit information on Mirabilis Design and what we have achieved over the years. So starting off with the use case one, the infotainment system. So here we will, in particular, we will look at the data access sequences and the subsystem configurations which are required to achieve the maximum performance within the constraints defined by the architect. So over here, we have the hardware software definitions for an infotainment system mentioned. Here we have the block diagram representation of the system, and here we have on the left hand side we have the system overview. So the sequence is as follows: the video camera is going to generate frames at a certain frame rate, and these packets are then stored into SRAM. And once they are stored, the DMA engine is going to read from the SRAM and is going to write to the DRAM. So once the data has been written to the DRAM, the CPU is going to get triggered to execute on this data. If it is a resource-intensive application, then the GPU is going to get triggered to execute on the data from the DRAM. Once the data has been fully processed, the display controller is going to read the data from the DRAM and then going to send it out to the display unit. So this is the sequence that is evaluated for this particular use case. So this is the system model representation of the infotainment system. Here we can see the video interface is here. The data video packets are being sent, and through the bus it goes to the SRAM. And once it is stored, we have the DMA engine, which is going to read from the SRAM and then goes through the bridge to the PCIe and through the AXI to the DRAM. Then here we also have a different subsystems, that is the ARM Cortex A53 core here. Then we have the GPU module and also the display controller. So once the processing is done, the display controller is going to read from this DRAM and then write it out to the display unit. So here we have done a use case analysis where we are doing an architecture trade-off study. So what we wanted to identify was what is the maximum number of packets that can be sent through the interface. So we try changing the number of packets sent per second, starting with the 21 packets per second, and we could see what was the latency observed. So with 21 packets per second, we get around 41.4 microsecond as the peak latency, around that range. And when we increased it up to, when we made a 10x increase in the number of packets, that is at 210 packets per second, we got about around 12 millisecond as the peak latency. So with 300 packets per second, we got a buffer overflow across the channel buffer. So we could identify that around 250 packets per second was the system limit, and increasing it further would crash the system. So these were very informative and provide insight to the architect, as it is done very early in the design process. So throughout the session, if anyone have any doubts or require more clarification, please feel free to ask in the chat window. I will look at them once a session is completed. Thank you. So for the use case 2, we will be looking at the system on chip design for a multimedia application. And this is the block diagram representation of our target system. And this is the two targets that or the requirements that needs to be satisfied. So here we from the block diagram, we could see it's an ARM Cortex A53 subsystem here. We also have a hardware accelerator for running resource intensive applications. And then we have the bus hierarchies and the memory is also located. So there are mainly two targets that we need to achieve with this design. One is the SoC power consumption should stay below 2 watts. And also the total number of frames in 20 milliseconds should be greater than 50,000 frames. So these two are the main requirements that we had set before doing the architecture exploration. So here we have the model, the same model developed in VisualSim Architect. Here we can see the hardware architecture. The ARM subsystem is here. The hardware accelerator is here. The system buses and the memories are located here. So at the bottom, we have the software architecture or the use cases defined, the sequences. So here we can see the sensor generates the data, read the frame, decode the frame. We do the video post-processing, render frame function, then format conversion, rotate frame task, and then finally display. So this sequence of task is executed on the hardware above. So they are mapped. So from the perspective of an architect, there are different levels of analysis that can be done. First is at an IP or an ARM level. So what we do is we evaluate the pipeline stages, what is the right ARM code to be used there, what is the right width, the data path width, or the cache width, memory width, what is the right width, or what is the right clock speed. Then we also evaluate what is the number of execution units required, what is the levels of cache. So all of these are done at the IP level. Then at SoC level, the architect will be more interested to evaluate what is the right number of cores that needs to be allocated for meeting the target while considering the cost trade-off. Do we need any accelerator for this particular use case? What is the cache memory hierarchy and the coherence protocols required? At the system level, we'll be more interested in the development of an entire system like an IoT device use cases or ECU or an integrated platform altogether. So now we'll be looking at the simulations that we have done on evaluating this SoC design in order to meet that two targets, that is the power consumption and the performance requirement. So with the first use case, we ran all the tasks on software, that is on A53 core alone. So this means that all the tasks I have listed here, sensor, read frame, decode frame, all of these were executed using the ARM processor core. We are not using the hardware accelerator for doing any processing. It is idle. So with that use case, we could see the power consumption is below 2 watts, which is good. But the performance, it is not very good, because we could see the peak frames that we have obtained is about 23.3 thousand frames, which is less than the requirement. So as per our requirement, we need to get above 50,000 frames. So it is not being met. So as a result, what we do is we look at the activities for each of the function and how much resources it consumes, how much period of time does consume the resource. So it was plotted and we could see that the rotate frame task in particular was found to be more resource intensive because it consumed the resources for longest period of time. So as a result, we ran another simulation. Now the rotate frame task was executed using the hardware accelerator, while all others were executed using the ARM Cortex A53 core. So we could see that the number of frames in 20 milliseconds is meeting the requirement. So a peak of 125.5K frames were achieved, but at the same time, the power performance is not is going above the threshold. So it goes above 2 watts, and thus it is not meeting the requirement. So two observations were made. The average power consumption is greater than the threshold, and Hence, there are two options for the architect mainly. One is to use hardware accelerator from another vendor. So if we try different options, then it is possible that we can bring down the power down to 2 watts and it satisfies the requirement. But it is going to be costly because they will have to replace out the existing unit they have. Then the second option is use the same hardware accelerator that they already have, but apply power management techniques to it. This idea came from the fact that in the case to plot, we could see the hardware accelerator engine. When we plotted the power across it, we could see that it is only active for a very short period of time. So if we apply the power management techniques to it, it is possible to bring down the power. So on case 3, we applied the power management on top of it, and we could see over time, the average power consumption stays below 2 watts, while the performance is not heavily affected. So as such, we met both power and performance requirements for this particular use case. So now we are going to look at that use case where we're going to evaluate automotive software performance, specifically response times, and then hardware utilization with and without failure being injected. So here we have the VisualSim representation of detailed AUTOSAR running on an ECU. We have the runnable task, the assigning of software components all defined. We can also monitor the aliveness of the task and whether the deadlines are being met. So while maintaining such metrics, we ran the simulation without injecting any failure, that is on the left-hand side, and we injected certain failures and run the simulation as well. Those are 2 failures were injected. One is memory corruption, and second is running concurrent spurious runnable execution task. So with these 2 failures injected on parallel, we could see that the delay kept increasing over time. We could see it goes up and up and up over simulation time increases, and also there is increased activity across the processing units. So for ECU 1 and 2 activity plot, we can see the graph is more thicker than on the left-hand side. And here we could also see that the ready to run task is increased steadily climbing up over time, meaning that it is getting ready to run, but it is not actually being run because of the lack of resources. So now that we have taken a quick look at the use cases and how it is done using VisualSim Architect, a little bit of insight onto what VisualSim Architect is. It is a GUI-based code-free modeling and simulation platform. And what we do is we provides a full coverage of electronics, starting from anywhere between mission level, network level, or any integrated or distributed systems, semiconductors, and software. So what we are looking at right now is to connect the SysML and requirement studies with a specific implementation plan. So people with existing SysML models and requirements, they can easily port it over to VisualSim Architect to do more detailed study and do architecture exploration to determine the right components to eliminate all surprises in the design process. So here we are going to look at how we are bridging the gap between the concept and the implementation and the features it mainly provides. So we are providing a global project view with a dynamic experimentation approach. So with this, you can get a full, we can understand the full scope of the project, because oftentimes people from different disciplines are working on the same project, and people needs to understand the whole process, what is the scope of the project at an early stage itself, so that you can link up every design teams all on a single flow. So it also helps you to optimize implementation, because this is done very early in the design process. So as soon as you have the requirements defined, you can start building create the future prototype to do architecture exploration. So by doing that, you can eliminate all the surprises that might come up down in the development cycle. And also it also helps you to keep a single specification flow where all the members involved in the project are aware of what all their interfaces are doing and whether the requirements and dependencies are satisfied throughout the process. So here we have a simple graphic explaining how the specifications are maintained, how the clients specify it, and how the internal users plan it to meet the specifications provided by the clients. So it's a looped cycle. So whenever the client makes a change, the internal users or the planning team needs to account for those and decide, discuss with the system engineers, performance engineers, and subsystem architects to meet or decide how to make the changes in order to meet those requirements. So at this time, they can do the evaluation or do the architecture exploration using the platform to determine what is the right topology for the network that needs to be placed, what evaluate different mission conditions, and evaluate upon protocol stack, maybe do the software implementation and determine whether the response times are being met, and so on. So this helps to determine, to evaluate the target use cases and eliminate any surprises that might come up down through the design process. So here we have the design flow defined. So on the top, we have all the inputs that is required. So the user can define the inputs. If the architect or the user has existing SysML model, then we can import the details from it. If the user doesn't have a SysML model already present, then we can define the requirements and the system behavior in the VisualSim Architect platform itself. There is no need to create a SysML model for getting started. Then the user can also input different configurations, like what is the scheduling algorithm, what type of block control mechanism needs to be done, and then can start doing the architecture exploration. So once we have the base model developed, the architect can inject different type of failures, can evaluate different use cases, run different workloads to evaluate how the system behaves to such situations. Then according to that, it is going to generate different statistics and metrics that is going to help the architect make decisions, important decisions based on for the trade-offs analysis. So the architect can again do the design analysis on software level, network level, or on hardware design level, where they look at dedicated design flows. So the multiple people from different disciples working on the same project can model their own specific part for the system, and later on can all be linked together under the same platform. So this is the list of library items provided by the VisualSim Architect. It goes from simple traffic generators to all the way to different processor codes, ARM series, RISC-Vs, x86, PowerPCs. We also have different types of memory controllers, memory types, different interconnects, buses. So all of these are reusable components which can be dragged and dropped by the user into their own design to start designing. So it makes the model creation time much faster than anything else in the market. So now we are going to look at the VisualSim methodology, where we map the description-based model to hardware architecture to evaluate performance, power, and safety. So here we have, as an example, we have selected the signal processing radar system, and here we have the different functions or sequences involved in this particular use case. So here we can see the ADC, then we have the different functions, function 1, function 2, detailed pulse compression, function 3, transpose, function 4, window FFT processing, and so on. So the main goal of this particular signal processing radar system is to estimate the moving target tracking and for the static target tracking. So we need to make the estimate for a moving target as well as a static target. So when we are simulating it, we'll be looking at, or when we're designing it, we'll be looking at the response times, the latency for completing the task. So here we have the, we are showing how the system definition is captured from the SysML. On top, we have the SysML layout. At the bottom, we can see a much more crisp, detailed definition for the same system. The difference being now we have the hardware architecture definitions being made in the VisualSim Architect, which is not present in the SysML. So all of these functions which are there now, it is going to send the triggers to the dispatcher, which is going to send the triggers to the perspective hardware module for processing. So here we are seeing how the requirements are imported from SysML. So these were the requirements specified on the SysML side. There were two requirements specifically. One was the ST means the static tracking flow latency should be less than 3 milliseconds. The moving target flow latency should be less than 2 milliseconds. So these two requirements are tracked in VisualSim Architect using a utility called Diagnostic Engine, and it reads a CSV file which keeps a record of the requirements. So we can see the ST flow latency, the constraint is given, the constraint value 3 milliseconds is also given here. For the MT, it is 2 milliseconds. So the requirements are being specified on the VisualSim side as well. So now this is the hardware architecture layout that has been defined. Here we can see the processing units, the shared bus structures, different clusters. Here we have a 4-core system, and here within that we can, within each of these cores we can see a DSP core, the S buses, the SOC bus, the linked ports between them, and the DMA engine for the data transfer between them. So since we have a lot of resources and different functions, we are making use of a CSV file to define the resources and the configurations to execute different functions. So here we can see what are the destination modules and destination devices, the destination cores, all of these, the priority of the task, everything is defined as part of the CSV file. So we ran the base model, which is using a clock speed of 600 megahertz, and these were the simulation results that we obtained. We can see the activity diagram to verify the activity across different resources, all the DSP cores, buses, and clusters. We can also see the power consumption for the entire system. We can see a peak power consumption of around 7 watt. We can also see that there's a lot of spikes throughout, meaning that different subsystems are being turned on and off over time. We can also see the throughput plotter, which shows about a peak throughput of about 30 megabytes per second. And the main metric being that the requirements are not being met. Here we can see this is the output from the diagnostic engine, and we can see that the requirements that we had defined as input are not being met. So the measured value is greater than 2 milliwatts here. Here it is also greater than 3 milliwatts. So both of the MT flow latency as well as the ST flow latency are not being met for this base model simulation. So what we did was, in order to find out the right parameter combination to meet the requirements, whether at all it is possible, what we did was we did a parameter sweep where we wanted to determine the optimal configuration that meets the requirement. So here we can see we created a batch file which has different parameter combinations. So you can see buffer threshold 1, 6 different clock frequencies. It's 400, 600, 800, 1000, 1200. So you can see for each parameter value update, there is a combination of possible sequences generated. So we run all of these combinations, and then the diagnostic block is going to keep tracking of the requirement. So for each use case, each parameter sweep we do, we can see it is going to generate an output file for each simulation. So you can see all the result file generated for different simulations listed, and also an overall results file, which is going to list out which are the run numbers and whether it pass or fail. So we could see a couple of runs which passed, but then it is up to the architect to make the decision according to the cost performance trade-off. So here we could see for this particular use case, we have to select run number 19 as it satisfied most of our requirements. And we could see that with run number 19, the frequency had went up to 1000 megahertz. So in order to meet the requirements, it was required that we increase the clock frequency to meet the target requirements. So then if we have a stringent power requirement, because when we increase the frequency, the power consumption is going to go above as well. So if it is not possible, then the architect needs to evaluate different resources. So right now we are using different DSP cores, but what if they replace it with the Xeon cores or PowerPC cores? So whether that is going to meet the performance while meeting the power constraints. So these are some questions that can be answered very early in the design process using this approach. So once we are done, we can generate the documentation. So this is not a static document. It's an interactive documentation with all the plots and results loaded into the documentation. So what we do is we go to the export and then we do the export to web, and it is going to generate a documentation of this format. So as we, the user or the viewer can just move the cursor on top of these modules, and it can see different parameters it had used to run the simulations. And if they click on any of the plotters here, they can see the stats that we had obtained. So even for people who don't, or even for the users, or even for engineers who doesn't have the tool installed, they can easily view what type of analysis was conducted to make easy decision. So a little bit information on Mirabilis Design. We are headquartered in Silicon Valley. We are a software-based company based in Silicon Valley, and we have development and support centers all over the world, especially in US, India, Taiwan, Japan, and Czech Republic. Our primary software is called VisualSim Architect, and it's a modeling and simulation software. The architects and engineers use it to visualize, optimize, and validate the system specification prior to the development. And this is the timeline through which the Mirabilis Design has traveled so far. We can see different achievements that we had made over the timeline as well. So here we have various awards that we had received recently. We were awarded the best simulator of the year and awarded the best at various conference shows. So over here, we are comparing the benefits on a single chart where the current design methodology is compared with the VisualSim proposed methodology. So we can see that about 40% of time and resources can be saved by adopting this methodology. This is because the model creation time is significantly reduced, because we have very huge library components which can be reused. And for creating custom components as well, we provide building blocks that can be used to create custom blocks. So we can cut short the model creation time drastically to focus more on the analysis side to find all the bottlenecks in the design and eliminate any failures or bottlenecks in the design. So with this, I would like to wrap up today's webinar session, and you can ask me any questions from now on. Thank you all.